Well, hello everyone. My name is Alex G, and this is what I'm going to call the first episode of something I'm going to try to do every week. Basically, I'm a MIT physics first-year graduate student. I'm studying astrophysics, and so when we went to our physics orientation, they told us there were kind of like three things they wanted us to do in this PhD. The first thing was that, well, obviously you're supposed to learn more physics through classes and research. The second thing was that they said we should, actually learn how to do research kind of in a productive way. And the third thing that they told us was that we should learn to communicate physics to other people. And I think that last point, learning to communicate physics, is really important to me. It's one of the reasons that I enjoy doing physics so much, is because I really think it's really neat and I really like talking about it. So, so that's why I decided to do this. Every week I'm going to try and talk about something, whether it's kind of a fun physics problem or something that I've been working on in my research, or maybe there's interesting physics news in the media or something, or really just anything that I think is interesting that's vaguely physics related, if at all. So I guess that's kind of why I want to do this. I was originally hoping that I could get like a webcam or screen capture or something like that going, but everything that seems to do that properly costs a lot of money, like somewhere between $50 and $200. So that's not going to happen. So onto the content for today, I guess. So at MIT Physics, the first thing we have to do when we arrive, like even before classes start, is we have to take quals, which is basically a 5-hour exam about everything in undergraduate physics. So I took that about a week ago, and it hasn't really been off my mind since then. So I decided, an easy thing I can do is just do kind of, talk about one of the practice problems that we did while studying for quals. So let's get to that. So I guess I should explain the problem. So what we have here on the screen is, on the upper left over here, which I'm about to circle in red, is we have a DNA molecule which is connected by n number of links. And the idea is that you can kind of unzip this DNA chain from the right, but each time you unzip one of the links, it costs an energy E over here. And so the question we're trying to answer is, if we're at a temperature T over here, our goal is to find S, the average number of broken links. It's hard to write up here. Okay, so this is kind of a relatively straightforward, statistical mechanics problem. So I guess I'll write it kind of the path down here. So the first thing we need to do is we want to find the average number of broken links. And so this is going to be just simply the sum of S from S equals 0 to n times P of S. And this is basically just saying, you have some distribution of probabilities of having S number of broken links. Oh, I guess I should add that you can only break from one side. You can't break, you couldn't do something like break this link over here, but not break those other two links on the side. So it has to only be kind of consecutive breaking from the right. And so that's why you can do this average. Basically, there are, you can either have none of the links broken, all of the links broken, or something in between, and that's indexed by this number S. And so the average number is just going to be that number times the probability of breaking that many links. And so from statistical mechanics, you know that the probability of S is equal to the Boltzmann factor, which is e to the negative energy of the state divided by tau. Oh, and I should add a definition here. Tau, I'm just going to define as the Boltzmann constant times the temperature. So it happens when you learn Statmech from Kittel and Cromer. So it's the Boltzmann factor times 1 over the partition function. And the partition function is just an overall normalization, which is the sum over all possible states, in our case s equals 0 to n, of all of the different Boltzmann factors, right? Es over tau. And so this notation is kind of a little confusing because I'm using s both as like a constant and also as the index of the sum, but hopefully that's clear. So, yeah, and so this is the basic setup. Once you figure this out, it's basically a lot of crunching to figure out what's going on. One thing I'm going to do here is I'm going to work in the n goes into infinity limit, so assume so in other words, we have like a really long DNA strand chain, and that's just going to make some of the math easier. I did it out without that, but it's really a pain. So, okay. I guess the last thing we have to realize is if it takes an energy E to break one link, then the energy of the S state is going to be just simply E times S. And that's because, like, if you count, each link that you break costs 1 epsilon to break. So if you break 2 links, that's going to take 2 epsilon, and etc. And if you break 0 links, that's 0. So yeah, so we will do this computation. So the first thing we want to do is calculate the partition function. So I'll do that over here on the right in green. So z is equal to the sum over all s of e to the minus s e divided by tau. And this is just a simple geometric series, right? It's sum of r to the n from n equals 0 to infinity. That's just simply equal to 1 over 1 minus r. And I know, I looked that up on Wikipedia all the time actually, but yeah, so pulling that out, we're going to say this z is equal to 1 over 1 minus e to the minus epsilon over tau. And notice this is epsilon, not epsilon sub s. And just to clarify, that's because this is the sum over all s of e to the minus epsilon over tau. All of that raised to the s power. I think it's kind of squeezing a little, but yeah. So that's our first conclusion. The second thing is then we have p of s is obviously just that times the Boltzmann factor. So I'm just going to go straight to calculating this average value. So the average value of s is equal to the sum of s equals 0 to, infinity. I'm treating n as infinity, of s times p of s, which is e to the minus s e over tau times 1 over z. And if you notice, z doesn't depend on s, so we can take that out. But this sum over here, which I'm going to highlight in orange, is probably something that you haven't seen before. And so I'm going to show kind of like a nifty way that you can evaluate this sum. So let me erase some of the work I've done up here. So I'm just going to erase this work I've done on the partition function so I can show you how I'm going to do this sum. So let's say we have, the sum from s equals 0 to infinity of s times e to the minus s x. And in this case, I've let x equal, when we plug it in on the bottom, we're going to let x equal epsilon over tau, but for now we'll just use it as x. So there's a nifty trick that you can do where you realize that this is actually the sum over all s of negative d by dx of e to the minus sx. Right, because if you do your chain rule over here, when you take this derivative, you keep the e to the minus sx, but then you bring down a minus s, and so that cancels with the minus sign to just make s. Yeah, so this is a kind of a nifty trick, and since this x and this s are independent, and we assume in physics that you can always do things like this, we'll switch the order of the sum and the derivative. So this will be equal to minus d by dx of the sum of e to the minus sx. So we know how to do this sum, right? That's just a geometric series like we did for the partition function. But we have to keep the derivative out in front. So this is 1 over 1 minus e to the minus x. Cool. And now you take this derivative to actually get what the real sum is, right? This is kind of a pain to take, but you do, the gigantic chain rule thing. So the first one is you square the bottom and put a minus sign. Squared, and then you multiply it by the derivative of the bottom, which is just e to the minus x. Cool. And so that's kind of a nifty thing that you can do to just take this derivative. So I'm going to plug that back in down here in purple. And so after we evaluate that, we end up with 1 over 1 minus e to the minus x, which is minus epsilon over tau, squared times e to the minus epsilon over tau. And then you multiply it by 1 over z, which is just 1 minus e to the minus e over tau. Cool, and you see that this term will cancel with this term over with the square down here. And you get that your final answer is just final answer. This is equal to, and so I'm going to multiply everything through by e to the positive epsilon over tau, and you get e to the epsilon over tau minus 1. If you've ever been paying attention to statistical mechanics, you'll see that this actually is the Boltzmann statistic distribution, but I think that I thought about that for a little bit, and I couldn't actually find a good reason why this should match up, because, well, anyway, I couldn't think of any good reason. Yeah, so that's our answer, but usually you want to figure out what this actually means, right? So I'll take two limits over here. So the first limit, let's see, I'll do that in black, or I guess I'll do it in red. So if the energy to break one link is much greater than the temperature, then you can, at first guess you're probably going to say, then none of the links are going to break because, there's not enough ambient energy to kind of break any of the links. And indeed you do see that S is equal to 0. And that's because the epsilon over tau goes to infinity, so you get a 1 over infinity minus 1, which is 1 over infinity, which is 0. And if epsilon is much less than tau, then you can Taylor expand. E to the x is about equal to 1 plus x. And so simplifying this over here, we have 1 over 1 plus x minus 1, so we end up with tau over epsilon. Yeah, so those are just that seems kind of reasonable, I guess, which is basically if your average ambient temperature energy is 5 times the energy it takes to break a link, then you're going to break 5 links on average, right? Okay, well that's it. Thanks so much, and yeah, hopefully I'll be back next week, maybe with a webcam. Great, thanks.